So we're seeing more objects out there. We're seeing more stars. Well, what properties can we pull from this? Not just, hey, this is what it's composed of. That's one of the exciting things we can do. But we can say things like, how fast are they rotating? Like, for comparison, here's our sun. Our sun does a full rotation in about 30 days. Whereas you can look at other stars, like the star Altair, that'll do one rotation on its axis in about 6 hours. So we're talking about these massive stars that have these rapid rotations. So everything we're going to discuss in this part is going to be what properties can we learn about a star. So let's start with a simple idea. I want to know how big a star is. But I'm going to claim to you, we cannot measure the diameter directly. And all right, I won't hold on to this for too long. Why can't we measure the diameters directly? They're too far away. All right? They're just too far away. These things are too tiny. We're not going to resolve. Even the best telescopes out there, you're not going to be able to have this perspective because you need to know the distance and how big your image is. So we're going to have to use other tricks. We're going to have to use other tricks to figure out how big the stars are in the universe. And I'll make this picture a little more complicated, but I do love this. So let's go back to that game again. All right, so let's consider two stars. This time I'm going to say the stars, they are the same temperature, but they're going to be different sizes. Hold on, I'm seeing a question. Do all stars have coronas? And that be a part of the diameter? Excellent. So yes, all stars will have an equivalent of a corona. Now, how far that corona, that atmospheric layer, expands will depend on the properties of basically how massive that star is. In terms of diameter, for stars outside of Sol, we tend to define the diameter as being the chromosphere layer, that surface layer. All right. So back to the slide. We'll have two stars. I'm going to say they have the same temperature, but one is a white dwarf, about the size of Earth, and one is going to be a blue giant, this gigantic mass star, hundreds of times bigger than our sun. So these two stars, tiny little object versus the big massive one, same temperature, but very different sizes. And so we'll look at the spectrum, and you notice the bands. All right, hold on, I'm seeing a quick question. Do hotter stars tend to rotate faster? I'll have to look that up. That is a tricky one about what patterns we've seen in stars. Wish I had a prop with me, but there's definitely a correlation to how gravitationally massive you are and how quickly you're rotating. And as the gravitational forces get stronger, the more massive something is. Think about Kepler's laws. You do start to move faster just because there's these greater and greater forces acting on you. So there's definitely a relationship between mass and rotation rate. Right. So come back to the bands. Same temperature, different size. Look at how narrow the bands are for the big star versus how wide they are for the little star. Right? So the narrow bands, think about this. The giant star, because of how big it is, that outer layers, they're going to be a lower pressure, low compared to this guy. So the giant star, because its atmosphere is spread out so wide, you're going to have more narrow spectral lines. Whereas the tiny star has this huge, remember the pressure, it's just squeezing it in. Right? That squeezing increases what we call energy bands, the range of allowable energies. So by increasing the pressure on the tiny star, the bands that are radiated or absorbed are going to be wider. So we're comparing two stars of the same temperature, and the difference in their bands is allowing us to infer the size of the stars. The spectrum's not just telling us the composition, it's telling us how big the stars are. Now on B, let's try and actually calculate the size. Here's one technique to do it. So once again, I'm going to do the game. I'm going to have two stars. I'm going to make them equal size, but different temperatures. Those stars that only emit outside the visible spectrum. So, all right, I'm seeing requests for me to go back a bit. So let me answer the question. Are there stars that emit only outside the visible spectrum? So let's think back to this picture, right? The star is going to radiate in an entire spectrum. You're actually going to have the visible spectrum, let's see here, way out here. And so the star is radiating in this whole range, but the bulk of their wavelength is going to be outside. So yes, there are stars that will have ultraviolet glows. You'll have stars of X-ray stars. We'll talk about stars that are glowing the X-rays. So you can have this wide range. All right. So I saw a request to explain this again. So let's go through this. Big star, all right? Big star, low pressure. Low for stellar sense, low compared to this guy. So big star, less pressure, more narrow spectrums. These lines are more narrow. Go to the tiny star. Tiny star, these bands are going to be wider because there's increased pressure. There's more energy gaps, right? Basically, the amount of allowable absorbable energies start to go up as I squeeze and press on these things. So these bands, they tend to get wider. So the emphasis here, the length of these bands, they are slightly dependent on the size of the star. That's the emphasis. I can look at two star spectrums and infer how big the star might be, or at least compare their sizes. So let's try and get a more formal way. Let's actually try to calculate the size of stars. So this time, two stars, they're going to make them the same size, but different temperatures. How can you tell the temperature again? So I will get to that in a little bit. There is a way for us to get the temperature of the stars. It's based on the peak. You're going to see that that curve I did earlier at the beginning of this lecture. You'll see that again. So you will be able to get their temperature. Emphasis. I'm going to say the blue one is the hotter star. So if I look at just one section of the star, hotter star, it has to radiate more photons. It has to give off more energy. It's a hotter object. So the hotter object has to be giving off more energy per area. Well, if there are more photons coming out of this star than this one, then this guy must be more luminous. So here's the emphasis. If I know the luminosity and I know the temperature, I can get the size of the star. Right? We talked about in our previous parts how to get the luminosity. You go magnitude to brightness. If you know the distance, you calculate the luminosity. Now, we just need to get the temperature. And then I'll get to your question. How do I get the temperature? It comes back to this plot here, right? Here's the thing. The temperature of the star. Stars, all of us, we're called black bodies. We all radiate equivalent to what's called a black body radiation. We give this whole range of wavelengths that we glow in. The shorter the wavelength, the higher the energy. As the object gets hotter and hotter, it's going to radiate in more and more peaks, right? There's a peak wavelength, right? Here's an example. I'll draw this one. Here's the peak wavelength of this object that's at 4,000 Kelvin. Or the peak wavelength of this guy at around 5,000 Kelvin, right? So if you can measure the peak wavelength, if you get that peak wavelength, then by what's called the Wien's displacement law, that's this guy, you measure the peak wavelength and you do 2.9, 10 to the minus third meters Kelvin per that wavelength. You calculate the temperature. So you measure that peak wavelength. By finding the peak wavelength that star is radiating, you know its temperature. And this ties into what we call the Stefan-Boltzmann law. And here's how it goes. We say, look, the luminosity, the amount of energy a star is giving off, well, it's equal to the surface area of the star, 4 pi r squared. 4 pi r squared. That's the surface area of a star, or r is the radius, the diameter of the star, if it helps people. Here's my star. There's my radius. All right. So if I know the radius, right? Well, I want to find the radius. I can find the luminosity from techniques we described before. I can get the temperature by knowing the peak wavelength of light emitted from it. All right. Here's a plot of that temperature luminosity dependence. The sigma here is called the Stefan-Boltzmann constant. And simple math, I just rearrange this formula and I get the radius of a star. It's just dependent on the temperature and the luminosity. And this is the game that we're going to keep playing. What information can I measure? What information can I calculate from that? So we've gone from magnitude. We've gone all the way up to, from magnitude, we can get how powerful the star is. By looking at the spectrum, we can get how hot the star is. Well, now I know how powerful the star is. I know how hot it is. I know how big the star must be. So we're just pulling more and more of these stellar properties out this way. Some other things that we can learn using our spectral lines. We can measure things like what's called the proper motion of a star. Get an idea what I mean by proper motion. A star could be coming towards us or away from us, and we measure that using Doppler shifts. Is the star like blue shifted, red shifted? That can tell us if it's coming toward or away from us. But the proper motion, let's say we're here, is the star transversing. That's what I mean by transverse. Is the star moving this way at all? This motion, right? This motion we can easily tell. The star is coming towards us, blue, away, red. By looking at the spectral lines, we actually can learn about its transverse. We can learn how it's moving across the sky. Put this in perspective. Here's the Big Dipper about 50,000 years ago. And about 50,000 years from now, this star is moving towards the right. These stars moving to the left. The Big Dipper is actually going to start unfolding. So you might notice the difference from this image to this image is 100,000 years. So we're not going to live long enough to measure proper motion, or at least for our meek eyes to be able to see it. But by looking at the spectral lines, we can calculate the proper motion of the stars. That's what these arrows are showing us. These arrows are showing us which way the stars are actually moving. And with that, we can calculate what the constellations will look like in thousands of years. Now we can get, coming back to that, rotations. We'll focus on the non-rotating star first. It's radiating a certain amount of light. And that light comes down to us, and we see a spectrum. We see the peak, boom, we've got the properties of the star. But if that star is rotating, look, some of the photons will be blue shifted, some will be red shifted. Yes, there is a color shift. There is a slight shift for the stars moving left or right. There's a slight shift in the spectrum for a rotating star. So we see, in this picture, we see the band has widened up a bit. We can see the band is widening up. So the peak, instead of being a nice big dip in the center, it's this lazier one. And so we can say, well, the widths. Measure the widths of these gaps. These widths gives us information on how rapidly that star is rotating. Now, before anyone types it up, I can just sense that these questions are coming. We've talked about the narrowing, the spreading of these spectrums of how wide is this. Didn't we just say before that it could be due to the size of the star? It could be due to its rotations. The full answer is it is a complex combination of all of those stitched together. And it's our job as scientists to sit down and pull apart. Is it the rotation? Is it its distance, its size? It's our job to pull all this together. All right. This is how we know Polaris will no longer be the North Star. So there's a question of going back. Is properties like this why we know that Polaris will not be the North Star? Almost, but actually, this is not the main reason. Let me pull up my little drawing piece here. All right. Here's Polaris, my very poor drawing of Polaris. And here's Earth's axis of rotation. Let me get into... So Earth is rotating... So these who aren't following, the question was, is the proper motion why Polaris will not be our North Star forever? And it's not quite that. So Earth is rotating this way around on our orbital axis. But what's going to happen in about 20,000 years is that Earth's rotation axis, right? Here's Polaris again. What's going to happen is that our rotation axis is going to tilt. Earth has a tilt in its motion. So it goes from rotating this way to this way. And basically the tilt in our rotation changes. And that's going to be why Polaris will not always be our North Star. It will sometimes be our North Star, and in a couple thousand years it'll be another, and eventually it might come back. All right. I love the questions that are coming, so please keep sending them in. Will that make our seasons more extreme? Will this tilt make our seasons more extreme? It definitely is a factor into the seasons. You can talk about how Earth's seasons or Earth's climate has changed over the millennia. We're talking geological timescales. And yes, Earth's tilt like this does have a slight bearing. Right. So, continuing on, properties we want to measure. How do we get the mass of the stars? How do I weigh it? I can't pull out a spring scale and put the star on the scale. So basically, there are two methods I'm going to talk about, right? One method, we look at the spectral class, we figure out what's the star composed of. I know there's hydrogen, to about this amount, helium, I know there's some calcium. Say, what are its components? How big is the star? Add up its mass, calculate its mass. You just say, how much is there? How big is it? There's its mass. Another technique, if we're lucky, is we can study binary stars, two star systems. So we're talking about two stars that are orbiting around each other. And think back to satellites, right? If you put a satellite in orbit around something, you can calculate the mass of the thing that's being orbited. And here's a very similar trick. I say here are two stars. They're orbiting around each other, and I'm going to start using Kepler's laws to start pulling that information out. So we're going to have a couple of different categories of what we call binary star systems. Emphasis, binary, I just mean it's two stars in orbit around each other. One of the categories we'll call our visual binaries for hopefully what's obvious. We can resolve the stars separately. We can actually see the two stars around each other. So let's go through this, all right? Basically using Kepler's laws. You're going to have a high mass star and a low mass star. They are going to orbit their common center of mass. So they're doing big orbits around that center of mass. So you look at Doppler shifts, right? You look at Doppler shifts in those stars' velocities, and you get how quickly they're moving around. From that, you can get the total mass of both stars, how quickly they orbit their center of mass. And so from this, we've got an idea of like the range of stellar masses, and we found that the lowest mass stars are about 0.08, about 8% the mass of our sun. Remember, circle dot is Sol, our sun. So low mass stars are about 0.08. The high mass stars are about 150 times the mass of our sun. So, other types of binary star systems we found out there, you can have spectroscopic binaries. So these stars, they're too far away. We can't separate the two. They're too far away. So they just look like two objects stacked on top of each other. And what we can say is, well, we can just do the spectroscopic shifts. We can't visually see the stars apart, but we can see these spectral shifts. So as the star is rotating, here's A. As A approaches us, it'll be blue shifted. And then, all right, so 1, 2, 3, 4. Follow star A. A is blue shifted. Basically, no shift in A. And then as it goes away, A becomes red shifted. And repeat. So, how do I measure the speed of these stars as they orbit each other? Well, you measure, here's the A as it moves around in the spectral line. You measure the change, the frequency of this rotation. And by measuring that, you get, well, how quickly A and B are orbiting around their center of mass. All right. I'm seeing a question on what are black bodies. Okay, quick answer. A black body is any object that's interacting with light. We are glowing photons right now. So a black body is to say that I am absorbing photons, I am emitting photons at an equal rate. All right, binary stars. Binary stars, two stars orbiting each other. That's what I mean. Binary stars means two stars in an orbit around each other. I see a question. Is it possible for A to block out B? Literally our next slide. So let's move on to that. So I'll go back a bit to summarize. Binaries we've talked about. Here are two stars orbiting each other. These would be visual binaries because we can see them. We can tell them apart. We have spectroscopic binaries. These stars would be too far away. We can't resolve them apart. But by measuring the spectral Doppler shifts, by measuring this Doppler shift, we're measuring how quickly they're rotating around each other. Now someone asks, well, could one star block the view of the other? Absolutely. We call them eclipsing binary stars. So let me pull up the little GIF here. All right. There we go. All right. So, what do I mean by eclipsing stars? They're rotating around each other and they pass in front of each other. So what's going to happen? All right. And our simplistic model will say, well, it's one star is going to be a lot bigger than the other. And as the smaller star crosses in front, it eclipses the other. As that eclipse happens, it's going to reduce the brightness of the star. Right? So as one star is going in front of the other, the brightness goes down. Then you can see them apart. Light curve goes to the top. And then one goes behind, the brightness goes down again. So you measure the time. You measure the time between these dips. That's telling you the period of rotation. And how deep these dips are. How deep these dips are? Well, that's related to how big the stars are. So the period is telling you how far apart the stars are. The dips are telling you how big the stars are. So, stitching all this information together, we're starting to pull plots of all the stars we see. Here we have a plot of mass in terms of solar masses and the luminosity. And we've noticed a pattern. We're starting to see patterns here as we do these types of measurements on all the stars we can see. We do that. We found about 90% of stars follow this relationship. About 90% of stars follow this relationship. And it's approximately that the luminosity of a star is proportional to its mass to the fourth power. Another way to phrase this. If I know how massive a star is, I know its luminosity. And the symbol here, this is similar, right? This is not an exact relationship. It's not an equation. But there is this relationship that exists here that by knowing the mass of a star, that's giving me information on its luminosity. All right. So here is a brief recap. I'm not going to read the slides. I'll leave that up for you. But just a quick summary of like the different properties, stellar properties we could find, and the techniques we've used in order to get them. All right.